Improving quality of explanation by local embedding perturbation. In a traditional classification model, the input instance is given to the model and the model gives its prediction. However, in some area, just the prediction is not enough. The user also needs to know why. If given the instance, the model is able to produce the prediction together with the explanation. The user will have a higher confidence to accept or reject the prediction. However, sometimes we may get some bad explanations. Here is an example of two explanations with different features. And the first one is a good explanation, and the second one is a bad one. Current framework for generating local explanations consists of three steps. The first step is to generate the synthetic neighborhoods of a given instance. And the second step is to label the synthetic datasets using the model. And the third step is to generate the local explanations from the synthetic neighborhood. The crucial process is the synthetic neighborhood generation, and different synthetic neighborhoods can result in explanations of different quality. Here is an example of good neighbors and bad neighbors. Assume the shapes are different classes and the sounding lines are the classification boundary. The task of learning explanation is to find a local linear model. The black points is the instance that needs explanation. Here are two different synthetic neighbors. In the first one, we can find a linear model that is close to the boundary, and the linear model generated from the second one is far away. Thus, we know the first one is a good neighborhood and the second one is a bad one. We employ the local intrinsic dimensionality LID to measure the quality of the synthetic labels. LID assesses the intrinsic dimensionality of a local data submanifold around a given instance. The intuition is that the synthetic instances in a good neighborhood should have similar LIDs as the instance being explained. For example, in previous dataset, the LID of the given instance is 1.54. The average LID of the instances in the good neighborhood is 1.73, and the average LID in the bad neighborhood is 3.61. We model the local explanation extraction as a constraint optimization problem. The goal is to find a local surrogate, and the constraint is that the LID of the synthetic labels is similar to the LID of the test instance. And there is no closed form solution, and we will propose a heuristic approximation. Our proposed method consists of 4 steps. The first step is to select k nearest neighbors of the given instance in the training data, and then fit a local embedding using the k nearest neighbors. And then we generate the synthetic neighbors in the local embedding. And the last step is to project the synthetic neighbors back to the original feature space. To conclude, synthetic neighborhood generation is a crucial process for local explanation generation. LID is a possible metric for the quality of neighborhood. The proposed method is an effective method to improve the quality of explanation by improving the quality of the synthetic neighborhood.